Hello everyone. In this video we are going to introduce bases and talk a bit about them. So our first question is simple. What is a basis? So this is going to rely on some observations that we've made thus far, and it basically boils down to this one fact here, that maximal linearly independent sets coincide with minimal spanning sets. So in terms of maximal linearly independent sets, we have this result. So we had the assumption that S is linearly independent and V is not an element of S. And then if we add V into our set, this remains linearly independent if and only if V is not in the span of S. So again, what is this saying? It says if we add things that aren't in the span, we maintain linear independence. Okay? So basically, as long as we haven't spanned the whole set, we can keep making a bigger and bigger linearly independent set, and thus the second we get a spanning set, and thus when there are no more options for things outside the span, we have reached a maximal linearly independent set. Okay? So that's coming at it from one side. So now let's think about minimal spanning set. So here we had no assumption on S, but just that V was not an element of S. Then in this case, the span of S union our new vector is equal to the original span if and only if V is in that span, the original span. Okay, so what is this saying? It's saying that basically if you add in a vector that's already in the span, you don't change the span, right? We don't increase it. And if we want to get toward a minimal spanning set, basically this is saying you can take out vectors that are dependent on the other ones without changing the span. And so you can continue to remove things until you have nothing that is dependent on other things in there, and thus, once you become linearly independent, you become a minimal spanning set. Okay? And so these two things together lead us to the definition of a basis. So a basis for a vector space V is a subset S of V such that S is 1, linearly independent, and 2, a spanning set for V. So the span of S is the whole vector space. Okay, so those two conditions combined means that S is a basis. So now let's talk about some common examples. So first of all, we of course want to talk about the zero vector space. And since zero itself can always be written as any non-zero constant times 0, this means that 0 is not in any basis, right? It is automatically linearly dependent. So what is my basis for my zero vector space? It's actually the empty set. So it has basis the empty set there. Again, this is more by convention. You can take this as definition that it's generated by the empty set. And basically the fact that you can't have anything more, namely the zero vector, is exactly what we said above, because we have dependence the second we have the zero vector. For Rn, we basically just look at getting a 1 in exactly one row of each column. And so we call this basis epsilon n, and we actually call these vectors, so this would be like E1, E2, all the way down to En, where your EI corresponds to a 1 in the ith row and zeros everywhere else. Okay, so this is what's called like the standard basis for Rn. For Pn, right, this is polynomials of degree at most n. We have a pretty simple basis given by the monomials all the way up to the nth power. And then for one more, for matrices, so I'll just do M 2 by 2, but you'll get the idea for it in general. So here we would look for 1 in exactly one entry and zeros in all the rest, similar to those column vectors up above for Rn. So for 2 by 2, we have 4 different matrices. And in general, if you have m by n matrices, you have m times n different ones in the basis. Okay? So proving these are bases is not very hard, and these are in really nice forms, and it's good to know these common examples and expect to see them showing up a lot. So next we're going to talk about how we actually show something is a basis. So again, for those standard bases, it seems somewhat obvious, but in general, it isn't going to be very obvious that things are either linearly independent or dependent, whether they're going to span. So let's take an example here. So if we even have something like 1, 2, and 3, 4. So this is on the small side for an example, of course. Now, linear independence is pretty easy here, right? Because I only have 2 vectors, and thus I know I'm only looking for whether it's a multiple or whether one is a multiple of the other or not. Here they're not, so it is going to be linearly independent. However, just the general process there again, right, is to solve the homogeneous system and see if the only solution is the trivial one, that is, the one where all coefficients are 0. And in this case, my row-reduced echelon form here does turn out to be this, and thus we would know that like C1 is 0, C2 is 0, and so these guys are linearly independent, right? We have pivots in both columns. Now, what about span, right? So I've got linear independence. That's one of the things. Now I need to show, is this a spanning set for R2? Well, I know what a general thing in R2 looks like, right? It's some AB. And so here we're basically solving 1, 2, 3, 4, AB, and seeing, okay, do we always get a solution? That is there always a choice of coefficients so that we can get exactly AB out? And again, you could use a calculator for this, but row-reduced echelon form in this case is 1, 0, 0, 1. And then over here we have 3 halves B minus 2A and A minus 1 half B. And so in this case, right, like this tells you exactly what the coefficients should be, and you will always have a solution to this system. And so this means that any old AB lies in the span of these 2 vectors. And so this is a linearly independent spanning set. This is a basis. So for your first exercise, I want you to show that this set of 3 column vectors in R3 actually is a basis for R3, right? So show it's linearly independent and show that it's a spanning set. And so then the other thing I want to talk about here is not just a basis for, our common vector spaces Rn, Pn, M, M by n, and so on, but what about subspaces of those, right? So consider the subspace here given by matrices of this form. So A, B, C, 0, such that A plus B minus 2C is equal to 0. So how do we find a basis for this? Okay, well, we've already done some things in terms of finding spanning sets for such things, right? It's like parametrizing. So here, I can use the fact that A plus B minus 2C equals 0 to see that A, for instance, is negative B plus 2C, and thus solve for one in terms of the others, right? So then I know what these things look like in general, right? So if I see A, B, C, 0, and I substitute that in, I have negative B plus 2C, B, C, 0. And I can get this in terms of just, B times, I have negative 1, 1, 0, 0, and C times 2, 0, 1, 0. And so I know that this space is spanned by these 2 matrices. Then the question is, are they linearly independent? And of course, the answer here is yes, right? Because again, I have only 2 vectors, and they are not multiples of one another. But if you wanted to go the long route, right? So again, these span my subspace S. You could just go kind of through this way, snake down, and put in the entries. So this would be negative 1, 1, 0, 0, 2, 0, 1, 0, and then solve this in row echelon form, and you'll see that there's a pivot in both columns, right? So we have a pivot here, and we'll have a pivot here, and so we are going to have the unique solution of all zeros, right? All 4 coefficients being 0. So this is linearly independent, and thus this is a basis. So now, for your second exercise, I want you to find a basis for this subspace of P2. So these are quadratic polynomials such that P of 1 and P of 0 are both 0. All right, thank you for watching.